Welcome to week 4 of thin film deposition module of fundamentals of material processing. In the previous 3 weeks of this module, we have discussed various techniques to deposit thin films, and in this week we will discuss how the thin films on a substrate nucleate and grow. What happens when the atoms or molecules of the source material, which either we have by sputtering or by thermal evaporation or chemical vapor deposition, when they reach a surface where they have to get deposited, what is the interaction and how the thin film starts to grow on a substrate. Okay. To start that, we should first look at what happens when an atom or molecule approaches a surface. Okay. So, an atom or molecule can either get physisorbed or chemisorbed. Okay. So, physisorption or chemisorption. Okay. So, by these two mechanisms it will get attached to the surface of the substrate. Now, physisorption happens by means of weak van der Waals forces. Okay. And chemisorption happens by bonding of between the atom or molecule of the thin film and the substrate. It could be either ionic bonding or covalent bonding. Okay. So, it can vary between completely ionic to completely covalent, and if we are have a metal thin film on a metal substrate, then we can also have a metallic bonds between them. Okay. Now, this graph shows how the potential energy of that atom or molecule changes as it approaches the surface. So, this is the distance from surface as it approaches. So, you can see that first it will get physisorbed, okay, and this is the energy of physisorption, this EP, which is around in the range of around 0.25 electron volts. Okay. So, this is energy, and 1 electron volt is approximate is equal to 1.6 10 to power minus 19 joules. Okay. So, this is the energy of physisorption. So, as you see that it will get attached and lower its energy by physisorption. Okay. And then there is if there is a reaction or a bonding happens between the surface and the atom, then it will get chemisorbed, and the energy of chemisorption is in the range of 1 to 10 electron volts. Okay. So, higher energy is required for the bonding, and in between this is process needs some activation energy. To lower its energy further by chemisorption, it will need some activation energy. It can be either by substrate heating or some chemical reaction. So, this activation energy has to be provided so that this atom or molecule goes from physisorbed state to a chemisorbed state, and which will be much more stable because of ionic or covalent bonding between the surface and the atom or molecule. Okay. So, this is the process in which this happens, and how does atom or molecule get adsorbed on the surface? There are different ways to describe how many atoms or molecules are being adsorbed. Okay. So, first one of this is called Langmuir isotherm. Okay, and this describes the coverage on a surface by formation of monolayer, okay, of add atoms. So, any atom which is coming to the surface is called add atom, okay, because it is being added to the surface. Okay. Now, the rate of coverage, how fast of monolayer forms, will depend on several factors. Okay. First of all, if an add atom is being adsorbed on the surface, it is equally likely that it can also dissolve. Okay. So, there is a competition between these two processes. Okay. So, the fraction of surface sites covered, which is number of atoms on surface divided by number of sites where add atoms can be adsorbed. Okay. Absorbed. So, this is a ratio of how many sites are covered. So, fractional coverage. Okay. So, this change in fractional coverage will depend on how much is the coverage first of all, and what is the rate of adsorption and desorption. Okay. So, this is KADS is the adsorption rate constant, which will depend on adsorption energy, okay, and KDES is desorption rate constant, which will depend on the energy of desorption, okay, and also P, which is the partial pressure of add atoms in the vapor phase. Okay. So, if there are more add atoms in the vapor phase, they are more likely to cover the surface of the substrate. Okay. Now, desorption will depend on how much is covered, okay, because no atom can be dissolved from an empty site, right. So, it depends on how much is the fractional coverage, while on the other hand adsorption depends on the empty sites 1 minus theta and what is the vapor pressure, what is the partial pressure of add atoms in the vapor phase. Okay. So, the fractional coverage rate of change of coverage will be given by this expression. Okay. Now, so this is a differential equation and which can be solved with an initial condition such that at time is equal to 0 there was no coverage at all. So, theta was 0. So, if we solve this differential equation with this initial condition, we will get this as theta, this expression which describes how the fractional coverage will change with time. Okay. So, this is a time, okay, and this factor k is just the ratio of adsorption to desorption rate constants. Okay. Now, so we want to know if we have kept a surface in some pressure P and the rate temperature is such that the K is the ratio of adsorption to desorption rate constants. After a long time, okay, we will have a steady state because some of the atoms will be being adsorbed and some will be dissolved. So, it will reach an steady state, and at that steady state that fractional coverage would be given by this. Okay. If you put d theta by dt is equal to 0 into this expression, and then you will get this, and this curves is called Langmuir isotherm. Okay. These are called isotherms because it is for a fixed temperature, because if you change the temperature your K will change. Okay. So, these are for the drawn for the fixed temperature. Okay. So, by fixing temperature you fix K. So, then theta will depend on the partial pressure. Okay. Now, it is noteworthy to see that you will not ever get complete coverage because of this expression, okay, because there will always be some desorption. So, this as soon as there is one add atom is dissolved, the site will become vacant. Okay. So, there will never be complete monolayer formation, there will be some sites left vacant always. Okay. Only if your K into P is much greater than 1, then theta will approach 1, like monolayer, complete monolayer. It will approach, it will never reach there. Okay. So, these are the Langmuir isotherm plots for different K values. Okay. So, as you see that as K increases, the monolayer formation close to 1 happens at the lower pressure. Okay. K is the ratio of K adsorption rate constant divided by K desorption. Okay. So, if adsorption is higher, so at lower pressure you will reach more fractional coverage. Okay. And this is theta, okay, number of add atoms divided by number of total sites. Okay. So, this is how Langmuir isotherm works, but since we are not forming only a monolayer, monolayer formation is just a beginning of thin film deposition process. We will be forming multi layers. So, there is another isotherm called BET isotherm, and BET stands for the initials of 3 scientists, Brunner, Emmett and Teller, who gave this isotherm. We are not going into the details of derivation, but this expression tells you what is the coverage volume in volume. So, this is total volume of adsorbed gas V over saturated adsorbed volume for monolayer thickness. Okay. So, this V infinity is the for a theta in terms of volume for given by Kp over 1 plus Kp, right. So, this is fractional coverage, but in volume. Okay. So, if everything is saturated, how much volume of a monolayer is being absorbed. Okay. P star is the saturation vapor pressure of the adsorbate at the temperature of adsorption. Okay. So, this is the pressure, there will be an equilibrium. So, what is that pressure at which there is saturation at the given temperature? There is no change in desorption and adsorption rate, and it is being fixed. Okay. C is a constant depending on heat of adsorption. Now, this heat of adsorption is the enthalpy or energy change of physisorption. Okay. And H1 stands for the first monolayer, and H2 is for the second monolayer or subsequent monolayer, because these two energies are different, because first monolayer is being adsorbed onto the surface and second or third monolayer are being adsorbed onto the same material. To give you a more pictorial view, if this is my surface, okay, I have drawn it not straight but slightly rough surface, and if my atoms are being adsorbed, so this is my for monolayer coverage, and then so this is the H1, the enthalpy of first layer formation, and then there will be some add atoms which will start to get adsorbed on top of this, and there will be desorption from both sides simultaneously, and the energy of or change in enthalpy of second layer or third layer adsorption is considered same, and this expression will give you what is the volume adsorbed, okay, in form of multi layers. Now, if we plot this curve for different values of C, so these are values of C, you can see how the if the pressure is low, it can only form one monolayer, because this is the saturation volume of one monolayer and this is total volume. So, it will reach 1, but if you increase pressure, it can reach many multi layers. Okay. So, this is BET isotherms. Again, isotherms are for, because these are at fixed temperature. Okay. Now, and C is fixed by temperature. C is a function of temperature. Okay. Now, these are used mostly for to know what is the surface area, how much gas can be absorbed onto a porous or non-flat surfaces. Okay. So, it has this BET isotherm has many applications beyond thin film deposition processes. Okay. So, these are the two isotherms which govern how the atoms will be adsorbed. Okay. But once they are adsorbed, they have to interact with the surface, get chemisorbed, okay, then it will form a thin film. Now, what happens when you have a thin film growth? So, you start with the surface, okay, and when the film starts to form, you will convert the surface into an interface. Okay. Now, surfaces are very complicated. Bulk we can understand easily, surfaces are much complicated because of the dangling bonds, the rearrangement between dangling bonds, the energies are different. Okay. Interfaces are even more so complicated. Okay. There are various forms of interfaces that can form. Suppose if my substrate is crystalline, okay, periodic arrangement of atoms. On top of that, I can have a very crystalline thin film, right, which carries the information of this into the thin film. Okay. So, this is one kind of interface which we can say that this is crystalline. Okay. And if we recall our epitaxial thin film growth were crystalline thin film growth similar to this. Okay. We can also have an amorphous thin film growth and amorphous interface. So, where amorphous or polycrystalline, okay, where the material being grown has no relation to the crystal structure of the substrate. Okay. So, these are just random sites where these atoms are being adsorbed of the thin film, and this would be amorphous. Okay. And we can also have interdiffusion between the two material, substrate and the thin film, such that there is no sharp boundary between substrate and thin film. In this case, if this was my substrate, the thin film will grow like this. Okay. And so, there will be some mixing of the different species. Some atoms might go into the diffuse into the thin film also, right. So, this will be my thin film growth. Okay. This will not have a sharp boundary, but due to interdiffusion it will have a diffused boundary, okay, diffused interface. Okay. And these type of thin films will have better adherence to the surface, okay, because they are interdiffusing, they are mixing with the material of the substrate, but they are still separate element. Okay. They are separate. They can also form a compound. Okay. Okay. So, what could happen? This material may react and form a different compound. Okay. These gases which may form a monolayer may then diffuse into this and form a different compound, a new compound. Okay. Such as silicon oxide. Okay. If you take a silicon surface and diffuse oxygen atoms into this at a higher temperature, the oxygen atoms will bond to silicon and form silicon oxide thin film. Okay. So, these are the various kinds of interfaces which you can expect. Along with this interfaces, you might have interface defects. Various kinds of interface defects might be present. It could be missing atoms. If it is a perfectly crystalline arrangement, then you can have some atoms missing in between, or you can have extra atoms which are just there. Okay. You can still have some of the dangling bonds at the interface. You can also have lattice mismatch which will create different kinds of defect that we had discussed when we discussed epitaxial growth. So, lattice mismatch will give rise to either strain in the film or dislocations. Okay. So, these are various types of defects which you can expect at the interface, and you can have processes such that you can eliminate most of these defects such that your thin film is very perfect. Okay. And you might also have stress in thin films. Okay. Now, so this is about interfaces. Now, we will go into the thin film growth. Now, our material has been adsorbed, it has created an interface. Now, it has to form a bond and really start to grow to form a thin film. Okay. So, while discussing thin film growth, we will discuss two different aspects. One is thermodynamic aspect and the kinetic aspects. Okay. Thermodynamics aspects are more like equilibrium aspects that and it depends on energy. Kinetic aspects on the other hand relate to the rate of change. Okay. So, first we will discuss thermodynamic aspects, and in this dynamic we will discuss capillarity theory of heterogeneous nucleation. Okay. We all know that if we have a supersaturated solution, there is nucleation formation and the crystal growth. Okay. But that is a homogeneous nucleation in a supersaturated solution or supersaturated vapor phase. Now, this is a heterogeneous nucleation, which means nucleus of a different material is nucleating on a substrate of a different material. So, there are two different materials involved. Nucleus material is different and substrate material is a different material. Okay. Now, if a nucleus forms, so suppose this is a cap shaped nucleus which is formed onto my surface, and this is a collection of several atoms, okay, and multi-layer. So, once this nucleus is formed and it is not either spherical or hemispherical, say it forms an angle theta. Okay. So, this is an angle which it forms. So, it is not so we will see the relation with theta. Okay. So, once this nucleus is formed, there are two extra interfaces are created. One is this interface between the thin film, this nucleus and the substrate, and extra surface which is created, which is this surface. Okay. Along with that, there is some change in free energy which relates to volume. Okay. And along with that, because of this different surfaces, there is different surface energy or interface energies between these dissimilar interfaces. So, we need to take into account these surface energies also. Okay. So, now if I were to write what is the change in free energy by volume, okay, of this nucleation of this thin film of this formation of this nucleus. I can write this in terms of A3 R cube delta GV plus A1 R square gamma FV plus A2 R square gamma Fs minus A2 R square gamma SV. Okay. Now, let me explain these terms. This A3 it is a volume term, right, because and volume changes with R cube. So, this is a factor which affects the volume if multiplied by R cube gives the volume of that nucleus, because this nucleus it is changing from vapor phase to a liquid or solid phase, right. If it is a solid nucleus, then it is vapor to solid. Okay. So, that free energy change, sorry, this is not there. So, this is the free energy change of volume, right, phase change, okay, and this A3 can be given by 2 pi 1 minus cos theta. This will depend on theta angle, okay. Now, A1 is the energy of curved surface. A1 is equal, sorry, my mistake here. Let me start with A1. A1 is the energy of the curved surface. If we go back, this energy, so this is my A1, okay, this curved surface, okay. So, and this will be 2 pi 1 minus cos theta, okay. A2 is the energy of this interface, okay. So, this is my area of this interface. Now, if you see here, I have A2 at 2 points, right. So, this surface interface is being formed and A2 will be given by pi sine square theta, okay. So, now this interface is being formed when a nucleus is formed between film and substrate, okay. So, in this F is film, S is substrate and V is vapor phase, okay. So, interface is being formed, so this energy is added, and interface between substrate and vapor is being eliminated. So, this energy, surface energy is it's decreased from this, it's not it's subtracted, okay. Now, if you check here, once this area is covered by film, right, it is no longer, this area of substrate is no longer in contact with vapor, right. So, this surface energy is gone, but there is a new interface. So, that surface energy is added, okay. And A3, which is given by pi by 3 2 minus 3 cos theta plus cos cube theta, okay, is the this into multiplied by R cube is the volume, okay. So, this is the total energy change when a nucleus which forms an angle theta from the substrate is formed, okay. Now, if we were to compare this with the homogeneous nucleation in a solution where the spherical nucleus is formed, then we can say that this delta G in that case would be 4 by 3 pi R cube, the volume of the nucleus, change in free energy per unit volume, plus 4 pi R square, the area of the that sphere, and thus surface energy of that, right. So, these two are very similar. It is just for a nucleus which forms an angle theta and it is a heterogeneous nucleation, and this is for homogeneous nucleation, okay, in a supersaturated solution or supersaturated vapor phase, okay. Now, if we go back, we see there are these forces. Okay, these forces are surface energy, or you can say surface tension forces. Okay, which tries to keep the material together. We know that a sphere of or a bubble, a soap bubble, is formed because of surface tension forces, right. So these are just those forces, and if different forces are acting on this point, this surface energy or surface tension forces, then there should be an equilibrium between these forces, and which is given by Young's equation, which says that for equilibrium SV must be equal to gamma Fs plus gamma Fv cos theta. Okay, or from this we can say that cos theta, the angle which this nucleus, stable nucleus, will form would be gamma SV minus gamma Fs divided by gamma Fv. Okay. Now let us go back to this diagram once again. We can write this expression again here. So gamma SV, right, should be equal to gamma Fs plus the cos component of gamma Fv, right, cos theta, if we have force balance in x direction, right. So we can write this, and this is my Young's equation which I have written here. Okay, and from this we can calculate what is the angle of that nucleus onto my surface. Okay, this theta angle is also called wetting angle or contact angle. Okay. Now since there is a change in free energy, for the nucleus to be stable, this change in free energy with respect to the size of the nucleus should be 0. Okay. We know that as this nucleus is forming, it may also because of its energy, it may also dissolve, right, it will go back. So what is the energy minimum requirement for this to be stable? Okay. For stable nuclei, we should have d delta G over dr. The change in free energy should be equal to 0, okay, or less. Okay. So first, so d delta G over dr should be less than 0. So free energy should decrease with increasing radius of the nucleus, then it will be stable. Okay. And this is the critical radius. Okay. So if because there are several terms, some increase and some decrease. Okay. So at a critical radius and beyond, this nucleus will be stable. Okay. And this is the r star, the radius of critical or the critical radius of that stable nuclei. Okay. So we can, from this expression of delta G, we can calculate these values. R star will be given by minus 2 A1 gamma Fv plus A2 gamma Fs minus A2 gamma Sv divided by 3 A3 delta Gv. Okay. So this is the critical radius of stable nuclei, and the energy for this, the energy required for this nuclei to become stable is 4 A1 gamma Fv plus A2 gamma Fs minus A2 gamma Sv cube divided by 27 A3 cube delta Gv square. Okay. So this delta G would have a behavior like something like this, right. So, and this is R, okay. Delta G would have a behavior like, for nucleation and growth, let me if R is 0, then there is no change in free energy. So, it will be like something like this, okay. Sorry, this R, okay, and this is delta G star and this is R star, okay. So, if it when R is increasing, right, due to growth of the thin film, if it crosses this barrier or this radius, then the free energy change will be negative, and then your thin film or nuclei will be stable, okay. So, let us stop at this point, and in the next lecture we will pick up from here. Thank you very much.